Welcome to the deep dive. Today, we're not just, analyzing a brilliant scientist. We are really trying to dissect the mind that gave us the key to the modern world. We are diving deep into the sources chronicling the life and physics of Enrico Fermi, the man whose work it bridges the purely abstract world of quantum mechanics with the terrifying, tangible reality of the nuclear age.
In Fermi, born in 1901, he was working in a physics landscape that was it was transforming almost daily.
Right.
Yet, in that short lifespan, he earned titles that really define his epoch. Architect of the nuclear age, architect of the atomic bomb.
Yeah.
But I think the most evocative title comes from his colleague, Emilio Segre. He called Fermi the last universal physicist.
And that title, I think that is the core of our deep dive today. It means he was one of the incredibly rare 20th century physicists who didn't just excel in theoretical physics.
It's chalkboard stuff.
Exactly. The deep thought, the mathematical models, all the abstractions. But he was equally brilliant, equally capable in experimental physics.
The hands-on mastery, the actual building, the testing.
He mastered all of it, all of the physics of his day in theory and in practice. It's just, it's incredible.
So our mission today, based on the diverse sources you've shared with me, is to guide you through Fermi's intensely complex journey. We're going to try and extract the scientific nuggets, if you will, that fundamentally shifted the course of world history and physics itself.
And we promise a clear structure, some engaging detail. The goal here is for you to feel well-informed, not completely overwhelmed by the sheer volume of his genius.
That's a lot to take in.
It is. We'll chart his journey from a self-taught Roman prodigy, explore his foundational work on the statistical behavior of matter, his groundbreaking theory of the weak nuclear force.
Which is a huge one.
His pivotal role in achieving the first self-sustaining nuclear chain reaction, and then finally, his surprising philosophical musings on everything from, extraterrestrials to human maturity.
Okay, let's unpack this journey, starting with the almost unbelievable dedication that defined his formative years in Rome. I mean, how does someone become the last universal physicist?
Well, it starts with an intellectual spark so bright it had to be fueled almost entirely by self-education.
Right.
He was born in Rome. His father, Alberto, was a key figure in the railway division, and his mother, Ida, was a teacher. And he had an older brother, Giulio. The sources say they were incredibly close.
Yeah, they paint a picture of them sharing these deep intellectual interests, especially around mechanics. They were building electric motors, playing with these complex mechanical toys together.
But that early life was profoundly scarred. In 1915, his brother Giulio tragically died during a minor operation on a throat abscess.
And the sources really suggest this was a defining trauma for Enrico. That loss just fueled an already deep drive for, solitary intellectual pursuits.
And the most vivid early anecdote about his genius, it comes from this exact period of intense self-study. He made this remarkable discovery at a local market in Campo dei Fiori.
Read the book. Yeah.
He found a monumental 900-page physics book written entirely in Latin.
Wow.
Elementorum Physicae Mathematicae. It was a work published by a Jesuit professor, Father Andrea Carafa, way back in 1840. He didn't just buy it, he devoured it.
Let's just pause on that for a second. Think about it. He's not just learning classical mechanics. He's teaching himself an entire intellectual framework through a dense 19th century text and navigating its complex mathematics and scientific ideas in Latin.
As a teenager.
As a teenager, mourning his brother. It just shows an extraordinary capacity, not just for memory, but for assimilating these high-level concepts completely independently.
And this intense self-driven learning, it didn't go unnoticed. It led to his first real significant mentorship with Adolfo Amide, who was a colleague of his father. So around 1914, Fermi, who's still just 13, starts quizzing Amide on these really sophisticated geometrical concepts.
And Amide, he recognized that this was no ordinary boy. He gave him a standard textbook on projective geometry.
Which is not easy stuff.
No, it's complex. And what did Fermi do? He comes back 2 months later, having completely solved all the problems in the text.
All of them.
Every last one. Amide was, astonished. He labeled him a prodigy right then and there, and immediately shifted Fermi onto even more advanced texts on calculus and classical mechanics.
It's noted that Amide often said Fermi didn't even need to keep the books. His retention was just that complete.
And this foundation, this ground-up, self-taught mastery of classical physics, that's what allowed him to jump immediately to the cutting edge of quantum theory when he eventually got to university.
That university was the elite Scuola Normale Superiore in Pisa. In 1918, having skipped his third year of high school entirely,
Wow.
Fermi applied. The competition was fierce, and the entrance exam included this famously difficult essay question, specific characteristics of sounds.
Right. Most students would have written, a descriptive essay.
Sure.
But Fermi, he approached it as a pure physics problem. He chose to use Fourier analysis, a highly advanced mathematical technique.
Very advanced for a 17-year-old.
Oh, absolutely. He uses it to derive and solve the partial differential equation for a vibrating rod.
And the examiner, Professor Luigi Pucciandi, was utterly floored. He called the 17-year-old in and, according to the sources, told him he could have done just as well writing the examination a decade later. He said with absolute certainty that Fermi would become an outstanding physicist.
So he gets to Pisa, starts in mathematics, but then quickly switches to physics. And the coursework, it just wasn't enough for him.
Right. The Italian university system hadn't quite caught up to the revolutions of quantum mechanics and general relativity yet.
So Fermi just taught himself. He taught himself these cutting-edge concepts. His own director, Pucciandi, famously admitted that he often found himself asking Fermi to teach him.
To teach the senior faculty.
Yes, he'd organized these informal seminars on relativity and quantum theory, and they were led by the undergraduate student.
That self-taught mastery led directly to his foundational theoretical papers between 1921 and 1923, and they show this breathtaking grasp of relativity. For instance, in his first paper, he addressed the concept of mass changing with velocity.
He did this by expressing mass not as a scalar, just a number like 10 kilograms, but as a tensor.
Okay, let's unpack that for you because that is a key nugget of insight into Fermi's mind. Why a tensor? Why did he need to use that?
Well, in classical physics, mass is just this fixed, simple quantity. But in Einstein's special relativity, the effective mass of an object actually increases as its velocity approaches the speed of light.
Right.
So Fermi realized that to correctly handle the momentum and energy of moving systems within relativity, especially complex systems with electromagnetism, you just couldn't treat mass as a simple number anymore.
So by using a tensor, which is, it's a mathematical construct for things that need multiple components and directions to define them in space, he was signaling that mass wasn't static.
Exactly. It was dynamic, it was directional, and it was fundamentally linked to velocity and external forces. He immediately resolved these apparent contradictions between classical electromagnetic theory and relativity just by applying this more advanced mathematical framework.
And that paper was so significant, it was immediately published in the reputable German journal Physikalische Zeitschrift in 1922.
Then another breakthrough came with his introduction of Fermi coordinates, also in 1922. He proved that on a world line, which is the path an object takes through space-time, the space immediately local to that path behaves as if it were a flat Euclidean space.
Okay, so why is that idea so crucial for, practical physics?
Because it bridges this huge gap between general relativity, which deals with curved space-time and gravity, and our observable local world, which seems flat and well-behaved.
I see.
Before Fermi, trying to calculate the motion of a local object using the full machinery of curved space-time was, it was prohibitively difficult. Fermi coordinates provided a practical mathematical justification for physicists to use simpler, familiar Euclidean geometry when analyzing phenomena close to a moving object. It made general relativity testable.
And here is where this abstract theoretical work gets really interesting, and it connects directly to the future of the planet. While he was working on an appendix for an Italian translation of a book on Einstein's relativity, this is in 1923, Fermi was the first person explicitly and mathematically to point out the enormous amount of nuclear potential energy to be exploited hidden within the EFC22 equation.
Just think about the timing of that. It's 1923. Fission hadn't been discovered. The neutron hadn't been discovered. Rutherford had only just recently demonstrated the first artificial transmutation of a nucleus.
And yet, Fermi mathematically graphed the sheer potential energy that was just sitting there inside atomic nuclei.
He saw the potential for nuclear energy 2 full decades before the first nuclear reactor was even built. But he coupled this recognition with this extraordinary sense of caution.
He did. He immediately noted that finding a way to release those dreadful amounts of energy was not yet possible, which he considered, and I'm quoting, all to the good.
And then he ends with this very dark, very dry joke, writing that the first effect of such an explosion would be to smash into smithereens the physicist who had the misfortune to find a way to do it.
That's just a profound mix of scientific recognition and this self-deprecating humor about the monumental implications. It really shows a mind that was already anticipating the world-altering nature of his field.
He earned his degree at 20 in 1922. And the stage was really set for his great theoretical triumphs after a period of study abroad.
Yeah, his studies took him to these intellectual powerhouses. He spent time under Max Born in Göttingen, where he crossed paths with Heisenberg, and then later with Paul Ehrenfest in Leiden, meeting both Lorentz and Einstein.
And these experiences, they cemented his reputation. When he came back to Italy, he started the work that would literally define an entire class of matter.
This was in the realm of statistical mechanics, and it followed Wolfgang Pauli's 1925 exclusion principle.
Correct. So Pauli's principle states that no two identical particles with half-integer spin-like electrons can occupy the exact same quantum state at the same time.
Right.
It was a revolutionary idea, but it really needed a robust mathematical framework to apply it to large, real-world systems like, say, gases or metals.
And Fermi supplied that framework. He applied the exclusion principle to an ideal gas in this crucial paper.
And that paper resulted in what we universally now know as Fermi-Dirac statistics, because Paul Dirac independently developed the same statistical formulation a little bit later.
So this body of work, it describes how particles are distributed in systems where they have to obey the exclusion principle.
To give you a sense of just how important this is, this statistical mechanics explained, for the very first time, complex phenomena like the specific heat of metals or the behavior of electrons moving through a conductor. I mean, in essence, it explained why metals conduct electricity.
So because of the exclusion principle, the electrons in a metal have to occupy distinct energy states, which gives rise to this characteristic energy distribution that Fermi-Dirac's statistics describes.
Yes. And the ultimate sign of the impact of this work is the name, the nomenclature. Particles that obey this principle, electrons, photons, neutrons, are now universally named fermions, after Enrico Fermi.
And particles that don't, like photons, are called bosons. To have an entire classification of matter named after you, that's the mark of a fundamental change in our understanding of reality.
He achieved this fundamental breakthrough at a remarkably young age. In 1926, at just 24, Fermi won a competition for a new theoretical physics chair at Sapienza University of Rome.
He was recruited by Orsa Mario Corbino, who recognized that Italian physics was falling behind and really needed Fermi's genius to revitalize it.
And Fermi immediately set about building an elite team. He gathered these bright students like Emilio Segre, Edoardo Amaldi, and Franco Rossetti.
The Via Panisperna boys.
Exactly. They were lovingly nicknamed the Via Panisperna boys, after the street where their Institute of Physics was located. And this wasn't a traditional university lab, it was a collaborative powerhouse.
What was the culture like there? What defined it?
It was defined by Fermi's teaching style, which was highly pragmatic and problem-focused. He gathered colleagues and grad students daily, not just to lecture, but to solve problems, often problems drawn directly from his own cutting-edge research.
He literally wrote the textbook for them, didn't he? He published Introduction to Atomic Physics in 1928, making the most modern quantum concepts accessible to his Italian students. He created an entire intellectual ecosystem.
And while building this team, he tackled perhaps the biggest theoretical puzzle facing physics at the time, the crisis of beta decay.
This was a genuine existential crisis for the field.
It was. When a nucleus undergoes beta decay, it emits an electron. But careful measurements showed that the outgoing energy of the electron did not match the initial energy.
It looked like the sacred law of conservation of energy was being violated.
Which would mean the entire edifice of physics was flawed. The stakes were just incredibly high.
So what was the solution?
Well, in 1930, Wolfgang Pauli postulated a kind of desperate solution. He suggested an invisible, neutral, low-mass particle must be emitted alongside the electron, and it was carrying away the missing energy.
And Fermi took this speculative ghost particle.
In 1933-1934, he developed a complete quantitative theory for it. He's the one who named the particle the neutrino, which means little neutral one.
Why was he so willing to bet his reputation on a particle that was, at the time, completely undetectable? It seemed like it existed only to save a mathematical law. What gave him that conviction?
His core belief was just in the primacy of the conservation laws. For Fermi, the mathematical certainty that energy and momentum must be conserved outweighed the empirical lack of evidence.
He just trusted the math.
He trusted the math. He believed that if the numbers demanded a particle, that particle had to exist, however elusive it was. He wasn't just guessing. He was building a whole mechanism based on field theory, which was a huge conceptual leap.
And his resulting theory turned out to be monumental.
It was. His theory, initially called Fermi's interaction, fundamentally described the weak interaction, one of the four fundamental forces of nature. It explained how the neutrino was generated during the decay process and, maybe more importantly, why it was so hard to detect.
It only interacts weakly with matter.
Right. It set the entire paradigm for particle physics. It explained the creation and annihilation of material particles.
What's fascinating, and what really speaks to the radical nature of his thought, is that anecdote about his initial publication attempt.
Oh, yeah. The theory was so new, so radical, that when he submitted his paper to the prestigious British journal Nature, the editor flat out refused to publish it.
What was their reasoning?
They called the speculation too remote from physical reality to be of interest to readers.
Imagine rejecting the description of a fundamental force of nature because it felt too much like science fiction.
There was probably a mix of indignation and wry amusement among the Via Panisperna boys, reflecting Fermi's own calm confidence. He just published the work in Italian and German physics journals instead.
It perfectly illustrates the intellectual risk he was always willing to take. He was so certain of his theoretical foundations that he was willing to accept rejection, knowing time would prove him right.
He was a theoretical titan. But now we move into the third phase of his career, starting around 1934, where he makes this dramatic pivot and becomes equally dominant in the laboratory.
Proving that title, the universal physicist.
The impetus came from Irene Joliot-Curie and Frédéric Joliot.
Yeah.
They announced they had induced radioactivity by bombarding elements with alpha particles. And Fermi saw this work and realized he could do it better and cheaper.
He made a critical, very pragmatic choice about his projectile.
Yes. He realized that using the recently discovered neutron offered a massive advantage over charged particles, like alpha particles or protons.
Because the nucleus is positively charged, so it repels other positive particles.
Exactly. The nucleus exerts this strong repulsive force, which means you need an expensive particle accelerator to launch charged particles with enough energy to penetrate it. But since the neutron has no electric charge, it feels no such repulsion.
So he could bypass the need for an expensive cyclotron entirely and still get deeper nuclear penetration using a simple self-made source.
Precisely. His team prepared a strong neutron source using radon mixed with beryllium powder in a glass bulb. And then, starting with aluminum, he just systematically worked his way through the periodic table.
And he induced radioactivity in 22 different elements.
Yes, a breakthrough that demonstrated a powerful new way to manipulate the nucleus.
This systematic bombardment eventually led him to the heaviest elements he could find, thorium and uranium. And here is where we hit a moment of, well, profound historical irony. The Nobel Prize won for a finding that was fundamentally a mistake.
A huge mistake. After bombarding uranium, Fermi believed he had created entirely new elements heavier than uranium. He even named them oscenium and hesperium.
And this work seemed so conclusive, so revolutionary, that in 1938, he was awarded the Nobel Prize in Physics for demonstrations of the existence of new radioactive elements produced by neutron irradiation.
But the reality, which he would soon discover, was that he had split the atom. He had created nuclear fission products, which are lighter elements.
And what makes this story so poignant is that the correct interpretation was actually offered years earlier.
By the chemist Ida Noddack. She suggested that the uranium might have shattered into lighter elements rather than simply absorbing the neutron and becoming heavier.
Wait, so if the Nobel Committee and Fermi himself, the greatest physicist of his generation, missed it, how could Noddack, a chemist who didn't have a sophisticated setup, have been right? What does that tell us about scientific ego versus just, simple chemistry?
It speaks volumes about the power of the prevailing theoretical paradigm. At the time, physicists universally expected that bombarding an atom would create an element higher in atomic number.
Okay.
The idea of a heavy atom splitting fission was considered theoretically impossible. Noddack, she was approaching the problem from a chemical analytical perspective, and she noted that the resulting products just didn't chemically resemble elements near uranium.
But because she didn't have a theoretical framework for how it could happen.
Her observation was dismissed. It was seen as chemically motivated but physically untenable. Fermi's interpretation held sway simply because it fit the expected model of nuclear physics at the time.
That is a potent lesson in how even the greatest minds can be, temporarily blinded by their own expectations.
But Fermi's neutron work led immediately to a far more consequential and correct discovery, the absolute necessity of slow neutrons.
This is maybe the most famous anecdotal turning point in his experimental career. The team noticed their experiments seemed to work significantly better on a wooden table rather than a marble tabletop.
Right. The wooden table seemed to enhance the radioactivity they were generating.
It sounds like pure luck, but Fermi immediately zeroed in on the anomaly.
He did. He remembered that other physicists, like Chadwick, had noted that paraffin wax was effective at stopping neutrons.
Oh.
So he repeated the experiment. He bombarded a silver sample first in open air, and then submerged the neutron source in the silver in paraffin wax.
And the result was staggering.
It was. When the neutrons passed through the paraffin, they induced 100 times the radioactivity in the silver compared to the control.
Wow, 100 times.
And Fermi realized that the hydrogen atoms in the paraffin, and similarly in the wood of the table, were acting as a moderator.
Okay, so how exactly does moderation work here, and why is that effect so pronounced?
It's all about collision physics, specifically something called elastic scattering. When a fast neutron, moving at high energy, hits a heavy nucleus like uranium, it barely loses any energy. It's like a tennis ball hitting a bowling ball.
Bounces right off.
But when a fast neutron hits a light nucleus, specifically a hydrogen atom, which has almost the same mass as a neutron, it transfers a massive portion of its kinetic energy and is dramatically slowed down.
So the neutrons, slowed to thermal speeds, are essentially just wandering around the uranium nucleus.
Exactly. And Fermi concluded that slow neutrons are captured 100 times more easily than fast ones. This is crucial because it allows the neutron to spend more time near the nucleus, which increases the probability that the nucleus will capture it and undergo fission.
He went on to describe this mathematically, right?
Yes, with the Fermi age equation, which provided the precise engineering tool needed to design a controllable nuclear reactor.
So he may have misidentified the products of fission, but his genius immediately grasped the mechanism for controlling the reaction itself. The discovery of slow neutrons is the direct theoretical precursor to the reactor.
Which brings us directly to the world-changing phase of his life, the Manhattan Project. The Nobel Prize ceremony in Stockholm in December 1938, it served as a necessary disguise.
Fermi, his wife Laura, who was Jewish, and their children, used the trip to Stockholm to permanently emigrate. They were escaping the harsh Italian racial laws under Mussolini.
They didn't go back to Italy. They traveled directly to New York City, where he accepted a position at Columbia University.
And his arrival in January 1939 coincided almost perfectly with the news that corrected his Nobel error.
Yeah, Niels Bohr brought the news from Europe. German chemists Otto Hahn and Fritz Strassmann had detected barium after bombarding uranium, and Lise Meitner and Otto Frisch had correctly interpreted this as nuclear fission.
The news must have been, well, highly awkward, but also scientifically clarifying.
It was described as a profound embarrassment that Ida Noddack had been proven right and his own transuranic elements were fictional. Fermi had to quickly add a footnote to his Nobel lecture, acknowledging that his findings were, in fact, fission products.
But the embarrassment was momentary. His focus immediately shifted to the implications.
His experimental skills were instantly crucial. Just days later, in January 1939, Fermi's team conducted the first nuclear fission experiment in the United States at Columbia's Pupin Hall, confirming the immense energy release.
And the immediate world-altering realization was the possibility of a chain reaction.
Right. Crucial experiments by French scientists suggested that when uranium is hit by one neutron, it emits 2 or 3 more neutrons. Fermi, alongside Leo Szilard, quickly verified this.
And Szilard, recognizing the devastating military potential, immediately pressed for secrecy and collaboration.
Fermi and Szilard were an unlikely pair, weren't they? One the calm, methodical Italian, the other the passionate, almost paranoid Hungarian.
Diametrically opposed in temperament and work habits. It led to constant tension, but they were bound by the shared goal of achieving a contained, self-sustaining reaction before the Axis powers did.
And Fermi's slow neutron discovery provided the technical key.
So how did that discovery shape the design of the reactor?
Well, Szilard initially favored a design using water as a moderator. But Fermi knew from his 1934 experiments that hydrogen atoms in water absorb too many neutrons. It just wouldn't work.
You can sustain a chain reaction using cheap natural uranium.
Right. Fermi's genius was in proposing a substitute, highly purified graphite, as the moderator. Graphite slows neutrons effectively, like hydrogen, but it absorbs far, far fewer of them.
This strategic choice was everything. It allowed them to proceed with natural uranium instead of the prohibitively expensive separated U-235.
It was the single most important engineering decision of the project. The resulting apparatus, Chicago Pile 1, or CP1, was built under intense secrecy and urgency.
And due to construction delays at the remote Argonne site, Fermi persuaded officials to build the reactor in the squash court beneath the abandoned stands of Stagg Field at the University of Chicago.
In the middle of a major city.
That setting just feels almost absurdly mundane for such a momentous event.
It was an incredible risk. The reactor was a stack of 40,000 graphite bricks, interspersed with chunks of uranium oxide and uranium metal. Fermi calculated every single aspect of the geometry and the materials meticulously.
And the famous date is December 2nd, 1942.
At 3:25 p.m., Fermi ordered the final control rod withdrawn, and CP1 achieved the first human-created, self-sustaining nuclear chain reaction.
A moment of technical triumph that just fundamentally altered humanity's relationship with energy.
The communication of the success is legendary. It really captures the secrecy and the weight of the moment. Arthur Compton, the director, called James B. Conant, and he used a carefully prepared code.
The Italian navigator has just landed in the New World.
To which Conant replied, "Were the natives friendly?" And Compton confirmed, "Everyone landed safe and happy."
That cryptic exchange signaled the arrival of the nuclear age.
And following CP1, the technology scaled up rapidly for industrial production of plutonium. Fermi was critical to the successful operation of these larger production-scale reactors. He was on hand for the criticality of the X-10 graphite reactor and then the much larger B reactor at the Hanford site in 1944.
And there, he solved a crisis that threatened to halt the entire war effort.
Yes, the problem of reactor poisoning.
So tell us what happened at the massive B reactor shortly after it started up.
The B reactor was enormous, designed for mass production of plutonium. It was running successfully, but shortly after starting up in September 1944, the power level mysteriously began to drop.
It just shut down.
The chain reaction ceased completely by 6:30 in the morning. Then it would start up again briefly, only to shut down hours later. They were caught in this baffling start-stop cycle.
So an unexpected failure that meant either a massive engineering flaw or a completely unknown physics problem.
Exactly. Fermi and John Wheeler quickly traced the problem to neutron poisoning by a fission product called xenon-135. X-135 is produced when fission occurs, but it possesses the largest known neutron absorption cross-section of any element.
Okay, explain that concept, the cross-section. What does it mean for xenon-135 to have a massive cross-section?
Imagine the target area an atom presents to an incoming neutron. Most atoms present a tiny target, meaning a neutron can fly through miles of material without hitting a nucleus. X-135, however, presents an absolutely enormous target. It acts like an incredibly efficient sponge, just soaking up huge quantities of the thermal neutrons that are necessary to sustain the chain reaction.
So as the reactor ran, it was producing this neutron sponge, which eventually soaked up all the available neutrons and caused the reactor to shut down. But why did it start up again later?
Because X-135 is highly radioactive and it decays, with a half-life of about 9 hours. So when the reactor shut down, the supply of new xenon stopped and the existing inventory decayed away.
I see.
Once enough of the poison was gone, the reactor could briefly restart, only to build up the xenon-135 again and shut down. They were caught in a cyclical trap.
So how did Fermi solve a problem of that magnitude in real time?
The problem was complex, but the solution lay in what the scientists had initially viewed as wasteful over-engineering.
Right.
The contractor, DuPont, had added 504 extra process tubes to the reactor core beyond the scientific team's original design, bringing the total to 2004. These were intended as a safety margin.
A safety margin that now proved essential.
Precisely. Fermi realized that loading all 2004 tubes with uranium fuel, including the extra 504, would provide enough excess reactivity, enough excess neutrons to overcome the xenon-135 poisoning and stabilize the reaction permanently.
That seemingly arbitrary design deviation saved the wartime production schedule.
It stands as one of the great quick-thinking engineering feats of the project.
Fermi became an American citizen in July 1944 and moved to Los Alamos, heading F Division. And this led directly to the ultimate culmination of his wartime work, the Trinity test in July 1945.
And at the first full nuclear explosion, Fermi performed his famous, almost deceptively simple field calculation to estimate the bomb's yield. This story, more than almost any other, demonstrates the mastery of the Fermi method.
Right. He didn't rely on the sophisticated diagnostic equipment, which was often unreliable or experimental. So what did he rely on?
His mastery of basic physics principles. As the blast wave swept past the observation bunker, Fermi brought out these strips of paper. He dropped the paper strips into the air, paced off the distance they were carried by the force of the blast, and then used that distance, coupled with his knowledge of fluid dynamics and shock waves, to perform a quick back-of-the-envelope calculation.
And the result of just dropping scraps of paper.
He calculated the yield as 10 kilotons of TNT.
Yeah.
The actual measured yield, derived from much more complex instrumentation and later analysis, was around 18.6 kilotons.
That's astonishingly close.
For such a crude field test, that level of accuracy is truly amazing. It shows his ability to distill the essence of a hugely complex physical event down to a simple, measurable parameter and generate a highly accurate approximation.
Following the Trinity test and the bombings of Hiroshima and Nagasaki, which Fermi learned about over the public address system at Los Alamos, the focus shifted from war machines to post-war academia and the question of humanity's future.
Yeah, he became the Charles H. Swift Distinguished Professor of Physics at the University of Chicago, establishing what is now the Enrico Fermi Institute. He continued crucial experimental work at Argonne, especially investigating neutron scattering.
His mentorship extended far beyond the lab, too. He helped Maria Mayer, a colleague at Chicago, develop her crucial insights into the spin-orbit coupling model of the nucleus, which later won her a Nobel Prize.
Beyond academia, he became an indispensable figure in science policy. He served on the influential General Advisory Committee, the GAC, to the Atomic Energy Commission, which was chaired by J. Robert Oppenheimer.
And this role brought him to his greatest moral and technical crossroads. After the Soviet Union's successful test of its first fission bomb in 1949, the political pressure in the United States to develop the hydrogen bomb, was immense.
The GAC, under Oppenheimer, was divided. But Fermi took a particularly strong and principled stand against the H-bomb's development.
He and Isidore Rabi co-authored a report that opposed the project on profound moral and technical grounds.
Morally, they believed a weapon of unlimited destructive power crossed an unacceptable ethical line. They argued it was inherently evil, regardless of the context, and that its development would just lead to a spiraling arms race, which proved tragically correct.
So that was his moral argument. What is his technical argument?
Well, once President Truman made the decision to proceed, Fermi, despite his moral opposition, remained involved to make sure the science was sound. He collaborated with Stanislaw Ulam, and they performed critical calculations that showed the initial design proposed by Edward Teller just wouldn't work.
How so?
He demonstrated that Teller's initial model would require prohibitive and virtually impossible amounts of tritium fuel, and that it would probably fail to ignite reliably anyway.
So his cold, pragmatic technical analysis forced the necessary revisions that led to the successful but far more complex later designs. He was indispensable whether he agreed with the mission or not.
Absolutely. Though he did testify on Oppenheimer's behalf during the infamous 1954 security hearing, a clear act of loyalty and principle, his main post-war scientific focus shifted dramatically. He went back to the truly fundamental questions of the universe: particle physics and cosmology.
It's remarkable how quickly he returned to the abstract. What were his key contributions to particle physics during this final period?
He did crucial work on mesons, specifically pions and muons. He made the first robust predictions of pion-nucleon resonance, which helped establish the fundamental interactions between these particles and the nucleus.
But even more groundbreaking was his speculation with Chen-Ning Yang that pions might not be fundamental particles, but composite particles.
And why was that speculation so ahead of its time?
It directly foreshadowed the later development of the quark model. At the time, physicists saw pions as indivisible. Fermi, relying on symmetry and energy conservation, his lifelong theoretical anchor, just guessed that they were made up of something smaller.
It just shows his intellectual ability to see the underlying structure that others missed, driven by mathematical elegance rather than empirical data.
He also tackled cosmic rays, didn't he?
Yes. He theorized that cosmic rays, these high-energy particles bombarding Earth from space, originated when material was accelerated by magnetic fields present in the interstellar medium. This theory, now known as the Fermi acceleration mechanism, remains foundational to modern astrophysics.
And throughout all this complex work, theoretical and experimental, the common denominator was his approach, the Fermi method.
His reputation for unerring accuracy earned him the nickname the Pope at Los Alamos, not out of piety, but because his physics pronouncements were considered infallible.
C.P. Snow famously wrote, "Anything about Fermi is likely to sound like hyperbole, because his brilliance just seems impossible."
The Fermi method, which is still taught in engineering and physics schools today, is that unique strategy of achieving quick, highly accurate, approximate answers using simple back-of-the-envelope calculations. It prioritizes physical insight and simplicity over complicated, lengthy computation.
It embodies his belief that if you truly understand the core physical parameters of a problem, you don't need all that excessive mathematical machinery. You can estimate the answer within an order of magnitude, often astonishingly close to the precise measurement.
And this self-assurance and belief in optimization, it extended into all aspects of his life. There's that famous anecdote that his self-assurance extended even to believing his method of cutting bread was superior.
Right, he once took the knife out of a colleague's wife's hand to demonstrate his philosophical approach to slicing.
It captures his personality perfectly. An intense focus on the simplest, most efficient solution for any problem, whether it was managing neutron flux in a reactor or achieving an even slice of bread.
But perhaps his most enduring philosophical contribution outside of nuclear physics came from a casual luncheon discussion at Los Alamos, the Fermi Paradox.
This is a classic Fermi method problem applied to the cosmos. The paradox addresses the staggering contradiction between 2 points. One, the high probability that extraterrestrial life exists, given the vastness and age of the universe.
And two,
The complete lack of physical evidence like probes or signals or colonization that such life has ever visited us.
the core question is famously simple. Where is everybody?
It's a rapid, logical, back-of-the-envelope calculation of the universe's potential versus its observable reality. And it yields this massive, unsettling contradiction that remains a foundational conundrum in astronomy and astrobiology today.
Sadly, his life was tragically short. He died in November 1954 at the age of 53 from inoperable stomach cancer.
The sources often speculate that his illness may have been related to his intense early work near the Chicago Pile 1 and other early nuclear apparatuses, before stringent shielding protocols were fully implemented. 2 of his graduate students who worked closely with him also died of cancer.
His short, impactful career was rightfully showered with honors. He won the Nobel Prize, the Medal for Merit, and he's one of only 16 scientists to have a natural element named after him.
Fermium, element 100, which was isolated from the debris of the 1952 Ivy Mike nuclear test. His name now defines institutions like the Fermi National Accelerator Laboratory Fermilab and the Fermi Gamma Ray Space Telescope.
But the true measure of his legacy might be found in his final philosophical warnings. Having seen the profound destructive power unleashed by his foundational work, Fermi worried deeply about humanity's capacity to handle the gifts of science.
He acknowledged that scientific advances always lead, sooner or later, to technical and industrial applications that revolutionize our way of life, just as his own work had. But he added this powerful warning, reflecting his deep concern about our collective wisdom. What is less certain, and what we all fervently hope, is that man will soon grow sufficiently adult to make good use of the powers that he acquires over nature.
That is a profound final thought from the man who delivered humanity its greatest power, and who, perhaps uniquely, understood the full spectrum of physics, from the theoretical elegance of the neutrino to the grim, tangible reality of the atomic bomb.
To synthesize his impact, Fermi was the essential bridge builder. He flawlessly connected the most abstract, pure theory, his statistical mechanics, his insight into space-time, his description of the weak nuclear force, with world-changing practical engineering, which culminated in the self-sustaining nuclear reactor.
And his method of critical, fast, approximate thinking endures as the hallmark of applied genius, proving that profound understanding can often negate the need for complex machinery. And that brings us to our final provocative thought for you to consider as you reflect on Fermi's legacy. He once drew a powerful parallel between his own work and Alessandro Volta's, noting that Volta, who invented the electric battery, had no idea where the study of electricity would eventually lead.
Right.
We know exactly where Fermi's study of the nucleus led. So considering Fermi's fear that humanity might not be adult enough for its scientific powers, a fear born from that transition from scientific innocence to scientific culpability, what contemporary scientific breakthrough, still in its theoretical or early experimental stage, holds the most dreadful potential power?
You mean something like genomics, advanced climate modification, or maybe the quest for artificial general intelligence?
Exactly. What breakthrough is out there now, forcing us to quickly evaluate our collective wisdom before it's too late? Something for you to mull over until our next deep dive.